Thank you, Paul and Eduarda, for this opportunity to share, well, some research that I've been conducting in the recent years on clustering time series data. So basically, what I tried in this talk is a little bit more data science, let's say, approach, not so technical as it would be, for example, in econometrics or in other kind of fields. Okay, so my idea is to explore a little bit the field, to provide some ideas, um, and sharing some thoughts with all of you. So I will start my the presentation. So basically, this is the title. So Paulo was already introducing the topic of the talk. So basically combines two of my areas, model-based clustering or finite mixture modeling, if you want to call that way, and time series data or panel data, if you wish. So this is the outline of the talk. So first I will start with the motivation for this type of research, what type of applications, what type of problems, and try to, in a bottom-up perspective, to introduce the reasoning or the underlying reasoning of the topic. Then I will revise shortly the finite mixture modeling or model-based clustering, just for some of you that might not be so aware of this model-based perspective. And then I will introduce, let's say, the core part of the presentation of this talk. That is more a tutorial than properly research-oriented talk on model-based clustering of time series data. So how can we cluster data when we have some dependency or some hierarchical structure? And then we have an application with COVID-19 data, and I finish with some conclusions and some potential ideas of extension of this type of approaches. Okay, so basically let's start with the motivation. But before the motivation, let's just clarify the perspective on this talk. So I'm taking a model-based perspective. So clustering can be a very general perspective regarding unsupervised learning. Typically can be on the grouping observations. That means, well, reducing, let's say, the data set into some prototypes or some pure members of the data set. In general, that is the idea. So when you are taking a more model-based perspective, we are assuming some kind of specification of the model. So typically, we are working with hidden or latent discrete structures. So basically, if you take a more continuous perspective, we end up in item response theory or factor analytic models. When we take a more discrete perspective, we end up in finite mixture models or latent class models. So that is the overall perspective. And then specifically in the context of time series, the clustering basically wants to find or wants to group units with similar stochastic dynamics, with similar patterns over time. So we have many applications of this type of techniques. So here I was just preparing, for example, number of papers published and indexed on Web of Science up to 2020. And you can see that, well, obviously clustering ends up to be a more general approach because, well, you can apply clustering almost to all kinds of data sets or data structures. Time series is also going up quite fast, but time series plus or and clustering or clustering of time series. This was just the Boolean keywords that I was. So it starts going a little bit, well, in the last, let's say, 6 years starts to grow a little bit. So a second motivation, apart from the perspective on the research, is also from the reality, from, let's say, the applied field, the problems we have to model, or we want to try to extract the hidden structure, the latent structure. So, and basically, this is just an example. For example, it's very well known in economics and finance, this kind of cyclical behavior of time series. So in economics, sometimes we call it a recession expansion economic cycle, for example. In finance, typically when we are dealing with stock markets, we end up using the bull-bear dichotomy. So that is quite often the case. In both cases, we are assuming just two regimes, just two, let's say, clusters. In the perspective, they are dynamic. So you can move from bull to bear and then from bear to bull, or keep in a persistent way in the bull state or regime. So in this case, we are assuming quite often a priori that we have, for example, just two regimes or just two clusters. So a recession expansion, so just two states, let's say, in state space, or you may end up with more states if you want to assume is not known a priori. So, and that might be the motivation. Let's imagine that we have, for example, let's say, time series of different stock markets. And we may want to cluster those sequences of time points. So is the Portuguese stock market, let's say, more similar to the Spanish stock market or to the New York stock exchange? So, and that is basically one of the motivations for this type of clustering. So, because, well, if they have similar patterns, probably you don't. If you want to diversify the risk, probably you don't want to buy stock with same kind of dynamics, for instance. Okay, so that is a second motivation to study this kind of contagious behavior, synchronization behavior, let's say, between different time series. A third motivation is based on a synthetic data set. So let's imagine this. So this is, in this case, I know the data generating process. So basically, I have some time series here. I know the real regime, the true regime of it at each moment. So, and we have different dynamics, you see. So the Markov chains, in this case, between the two regimes or two states, have quite different dynamics. So we can observe from the real, let's say, states that we have three clusters. We have one cluster, well, with very large persistence in same states, these, and these. Then we have one in between, these, and then this is very fast. That is very volatile, you see? So it switches between the two regimes in a very fast pace. So based on this, adding some, let's say, measurement error, I can obtain these, let's say, Ys, these observations. So here I have the observed process. Here is latent process that I just know when I'm simulating the data. I just know the clustering structure with simulated data because it is unsupervised. So now the problem is the other way around. Analyzing this data, can I extract the true structure? Can I reverse the process? So, and that is basically, can I identify from these time series that they belong to the same cluster? So that is basically the topic of this talk. So now let's start with model-based clustering just from a cross-sectional point of view. So because basically we'll have two layers. We have a layer that takes into account, let's say, the upper unit, let's say the country, the stock market, in which cluster it should be, let's say, allocated, or with quotation marks, classified, and then the modeling of the dynamics across time. So this is a very simple example. So let's imagine that we have this kind of data histogram, and we are trying to fit a normal distribution. So, but for example, if we try a mixture of two Gaussian distributions, so basically what we have the weights of the components, and we have the conditional distribution. So within, let's say, the first component that we can call cluster, the distribution is given by these parameters. Within second component or conditional on belonging to the second cluster, the distribution is characterized by these parameters. So we have basically in this very simple example, is a classical example from the time of the Pearson, with methods of moments that was very tricky to estimate, as you can imagine, some of you. So based on this, what we want is to estimate a mixture. So estimating a mixture, what we do obtain is something like this, you see. So we have one component, this component, that somehow captures the central part, and this skewness is captured by a second component. Let's say if you think about the perspective of clustering, we may say 30% of the observations are here, 70% are here, and these are the characteristics of the first component and second component. So this is just an application that we also can use finite mixture models as a kind of alternative to Gaussian kernels or other kind of density estimation. You see, so you can increase the number of components up to some limit that it almost becomes non-parametric in that regard. So basically, general definition of a finite mixture model, the simplest, the plainest one is like this. So basically, what we have is the mixture is basically the marginal distribution. Let's say summing up. In case of factorial models, we are integrating because latent variable is continuous. So is summing up a weighting sum of the conditional distribution. So if we want to represent the graph, is something like this. So given the latent variable z that is discrete because you are thinking about clustering, given the observation belongs to some cluster, so conditional on this, we expect to observe some y. So this is the distribution here. So the density within, let's say, component or cluster S is characterized by some theta sub S parameters. Might be mu, sigma, or some other parameters given the distribution. And these are the prior probabilities. So a priori, basically, is the mixing proportions or the size of the clusters or components, because basically is given by this. So what is the probability a priori of observing some individual, some unit of the sample from each component? So just to have some idea about the estimation, so typically nowadays, most of the applications of finite mixtures are estimated based on maximum likelihood. Well, and that, let's say, till the 60s, the method best known was the methods of the moment. But then, obviously, in 60s, with some approximation, some generalizations of the k-means and so on, this kind of iterative processes start to be more popular, and in the 70s with the EM algorithm that somehow was a generalization of all those approaches, things became very clear about the advantage of using maximum likelihood in this context. Because basically what EM does is to introduce some latent variables, basically. So you are assuming the cluster is a latent variable, and EM between the expectation and maximization, what somehow does is to integrate over the missing data that is the latent variable. So we don't know the labels. So basically we are doing that as a step in the EM algorithm. We also can use the direct optimization. The EM algorithm, as some of you have been working with, tends to be quite stable, but quite slow because the convergence rate is linear. So typically in my applications, what I do is I start always with EM algorithm because it's very stable in very flat areas of the likelihood surface or likelihood surface. But then after some point, when you have some density, some mass, then I jump to some Newton-Raphson algorithm because it's fast, it's quadratic, and you don't have problems of, divergence because of SCN matrices that are not regular and so on. Don't forget, so maximum likelihood in this context, they are quite, you have many modes somehow. And typically we have to repeat the algorithm many times to be with some, well, we are never sure, right? But to have to be almost sure that we are reporting the global optimum. But obviously, the solutions tend to be local. About model selection, typically in these models, we have to decide how many clusters, how many components, right? So apart from estimating, let's say, the pi's and the thetas, we also have to estimate the number of clusters, right? The capital S. So that is the part on model selection, how many components. So typically we are using information criteria. It has to do with some Kramer conditions on likelihood ratio tests. So basically, if you are testing on the boundary of the parameter space, so you can't use those kind of likelihood ratio tests. So typically, the same with time series analysis, for instance. So basically, what we do typically is to use BIC, archaic, and so on. So we have many indicators, but typically they belong to the same range of indicators. Basically, fit, likelihood, and some penalization to the complexity of the model. But you also have other alternatives based more on the number of parameters, entropy, uncertainty, this kind of thing. So we have a huge list of indicators to try to figure out the best solution. And sometimes in the end might be even the interpretability, right? So sometimes BIC may give you a large number of components because it's just picking some outliers as a component and so on. So it's a little bit tricky, but at least as a starting point, BIC is usually the best one. Now let's move to the core part of the presentation. So just after this, let's say, introduction of the finite mixture framework. So let's start the main part of this talk. So, and before starting the details, let's just introduce or revise or some concepts on conditional independence. So as you can imagine, these models are extremely complex because we will have many latent variables, and somehow we have to define some rules to simplify the estimation, to simplify the densities. Otherwise, we have multi-dimensional densities, and then even with the summing up, because we have to work on the marginal distribution. Don't forget, we have to integrate out or sum up over the latent states. So somehow we have to use some simplifications to make things operational and even, well, be able to estimate the models in due time. So the first easiest example for this kind of longitudinal data or time series data is a kind of Markov model. I'm using the Markov model because somehow I'm assuming the latent state as clusters. So somehow it's convenient to give the example of a discrete state space. So, and basically the Markov model is a simple model because, well, basically it's just conditional independent. If you fix one of the states, the other two states before and after are conditional independent, right? So you don't have a connection between them. So another model that is also frequent is again a mixture model or a latent class model. The difference is that in this example, I had just one variable, one y variable. So univariate data. So it was like here, I just have one dimension. But sometimes I have, for example, several indicators, right? I may have an indicator of income. I may have another indicator of years of education and so on. And I can have, let's say, a latent variable or a clustering, for example, based on social class. When the origin of the latent class model is from sociology, because they were just introducing the concept of social class. Social class is a latent variable. So, and it is, let's say, measured is built somehow based on several indicators. So this is the idea of the mixture model or latent class model. So we have several variables, and we are clustering. You are identifying some latent dimension that somehow conditionally explains the observed values. Notice they are conditionally independent. So in this case, these two values are conditionally independent. So if I know this value, these two values are conditionally independent. Notice this, for example, for some of you that have been working with Gaussian mixture models, for example, M-clust and so on. This is the case when the covariance matrices are diagonal, right? So all the covariances between different y's are 0, okay? So you are just modeling somehow the mu and the variance of each of these variables, okay? But this is a first model that now we can extend to the Markov model. So in this case, I'm assuming a Markov chain again, but Markov chain is conditional on a latent variable that is discrete. So this means that within each cluster, for example, within each cluster, I have a different dynamics of transition between states, for example. It might be, for example, based on job careers. Imagine job careers, unemployed, employed, unemployed, employed. So we have different individuals across time, a panel that is discrete. So you are observing discrete states. So this is the reason of the squares. Squares are observed, circles are latent or hidden. And basically, you want to use this variable to group somehow job careers of the individuals somehow similar because they have dynamics, transitions between states that are similar. Okay, so this is a third model, let's say, in this kind of building up process up to reach the model I would like to discuss with all of you. So a fourth model is very well known, hidden Markov model, or the regime switching model. So this is a very well-known model in economics, in speech recognition, in several areas, because basically, what do we have? We have basically a sequence, a time series, basically, and we are assuming this time series may have some noise, right? So basically, we have here a measurement model. So we want to remove the noise in this time series, for example, in speech recognition, or for example, when you have some sound and so on, quite often is used a model like this just to remove the noise from the environment. Okay, so cleaning the noise. And then what we have is the latent states, if you are assuming as discrete. So basically it might be like stock market. So if you are in this bear state, we are expect to observe, for example, high volatility and the stock markets going down. If you are in a bull, then you move to a bull state, then you expect, well, smaller volatility and for example, stock going up, you see. So notice this, all the observed values in this model are conditionally independent given the z's, okay? So if I condition on the z's, the y's are independent. That is very important characteristic for what comes next. So, and this is the model somehow that I've been working with. Is a combination of these two models. So basically, it takes into account the multi-level structure of the data. So it's a hierarchical or nested or multi-level, whatever you want to call it. And basically, we have units within units. So for example, the classical example of multi-level is students within schools, but also very well known is time series within, for example, countries. Or in panel data, we may have a sample of individuals, and then within each individual, we may have different moments or occasions of measurement, okay? For example, daily, monthly, and so on. So, and in this case, we have two dimensions of analysis. We may want to be concerned in clustering, let's say, the countries or the schools, for example, and clustering the students. Or I may want to cluster the countries based on the dynamics of the time series within. And so this is the idea of this model. So try to combine the two previous models. So this model was a Markov chain, a mixture of Markov chains. And this second part was the hidden Markov model. So if we combine the two, this upper part somehow measures the heterogeneity between, let's say, the countries or the individuals. And then here we measure the dynamics within each cluster, within each time series. So the first part will be a mixture model. So basically we have capital S clusters, and then we have a conditional density within each cluster. And the conditional density is basically all this sequence, and we will model it as a regime switching model. Because obviously, let's say, the conditional density is from y sub 0 up to y sub t. So we also have to somehow factorize that density into something more easy to work with. So this is basically the idea of the model. So in this model, we have three variables. The first one, the W, is a latent variable, but is time invariant. It means so a country belongs to one cluster and it doesn't move across time somehow. So it's always in that cluster. So it's a static latent variable. And we call it cluster, just to keep things simple. Then we have a dynamic, discrete, latent variable that we call state or regime. Typically, I call it more regime because of the tradition of econometrics. So, and then within each cluster, we have different dynamics over time, T. And then finally, I have the measurement model. So basically, the observed given all the latent parts. So this is also, let's say a terminology from latent variable modeling. So this part is the so-called structural model, and this part is the measurement model. So this is the connection between, let's say, the hidden model with the observed data or the observed reality. So basically, if we go back to the model, let's now try. So basically, we have to marginalize over all the latent variables. So the latent variables are the circles. We have to marginalize over. So the first part is the pi's sub s, like before. So is the size of the clusters, or the size of the clusters of countries, just to make things a little bit more well, specific. Then what we have here is, based on the graph of this model, we can simplify a lot, let's say, this kind of joint distribution of everything. So don't forget, this joint distribution is the distribution of all the data plus the W plus the Z, right? Then I'm summing up. So I'm marginalizing over the Y's. So what I have here is the initial distribution of the, let's say, the Markov chain. So it's just conditional on the W. Then here I have the Markov chain part. Notice some state, like for example, second here, is conditional on the previous one, and it is also conditional on W. So it's here. So the transitions between regimes depend on the cluster, on the belongingness to some specific cluster. And then finally, we have the measurement model. Don't forget, the Y's are independent, conditional on the regimes. So this is just a product of everything from 0 to capital T, and is given by this expression. So just to summarize, so this is the model. size of the clusters, initial probabilities, transition probabilities, and measurement component. In our case, we are just, to keep things a little bit simple, assume a Gaussian component. So this is the log likelihood is just, well, notice this. In this case, because we have lots of summing at the beginning, as you can imagine, use the log likelihood doesn't help a lot, right? Because you don't have products. And that is the reason why typically we jump immediately to the EM algorithm. So model selection here has to do with decision about the capital S number of clusters and number of regimes. So it's a bidimensional selection problem, not just like in the previous case with cross-sectional data that we just have number of clusters. Here you also have to decide number of regimes. Typically you are also using the BIC, so finding the best combination of capital S and capital K that minimizes the BIC. And then model estimation. As you can imagine here, EM is a little bit tricky in this context, and we use an extension of Baum-Welch algorithm. So Baum-Welch algorithm is very well known in estimation of hidden Markov models. So if you have just this part, we have to extend it because we also have the W. And then the application. So now let's see how this can provide some insights regarding some, well, real case, as you want to put this way. So I'm just illustrating with a, let's say, I would say a simple example. I'm using data from COVID, number of cases per 100,000 inhabitants from 194 countries. I'm using, so this is a panel, right? So this is my number of time points and number of countries, right? So basically what I want is to cluster these countries based on dynamics across this period. I'm using this period because this time series starts at different points, right? So the recording of, and it ends at this point because after this point, it starts just reporting weekly. And I'm modeling the growth. So I want to see the dynamics of going up, going down. So basically a kind of volatility in the time series. So based on the model selection, based on BIC, the best solution is with 3 clusters. So I have 3 sets of countries with different dynamics. And to represent each dynamic process, the best solution is with 3 regimes. So quite often we set up a priori, for example, 2 regimes. For example, the example I gave you, recession expansion or the bull bear markets. But in this case, I had no clue a priori about how many regimes I need. So let's just select, let's say, with quotation marks, the best number, and it was 3. So basically I have 3 clusters, and the dynamics within each cluster can be represented by the transition or the state space of dimension 3. So now let's start analyzing the results. So this is the prior probabilities of the clusters. So somehow represents the size of the clusters. Notice these are probabilistic. It's not a hard partition, okay? So so the first cluster is around one fourth of the sample. The second one is around half, and third is also one fourth. Okay, so second one is the largest one, so is almost half, or is half of the sample, and then we have some balance between cluster 1 and cluster 3. Then we also have the posterior probabilities. We can estimate the posterior probabilities based, for example, on the M algorithm or based on the Bayes theorem. So what is the probability of belonging to some, let's say, cluster, given that we did observe this data for this country? So some countries have posterior probabilities that are quite hard partition or crisp partition, in the sense that is like 0, 0, 1. So without uncertainty in the classification. So Afghanistan belongs with high probability to cluster 1. So this is the model, is the base criterion. So let's say allocate to the cluster with maximum a posteriori probability. So for example, Albania 2, Andorra 2, but then for example, some countries you can see here, some countries you have some mixing between these two clusters. So for instance, Lebanon was allocated to cluster, if you force somehow, hard partition, it is allocated into cluster 2, but well, it's not 50-50, but almost, okay? So sometimes it's interesting to understand this kind of countries or observations that somehow are stuck in the middle between two clusters, because they may have a kind of some characteristics of dynamics of one cluster and some characteristics of dynamics of another cluster. Sometimes, for example, it's difference of policies. Let's say around middle of the time series, the policy they change, and then you may have a different stochastic process afterwards. So half is from one side, half is from another side, something like that. Now let's try to figure out the dynamics or the characteristics within the regimes. So we know that the time series somehow is, let's say, represented by 3 levels, 3 states, 3 regimes. So, and these are the characteristics of the regimes. So this is the marginal distribution of the probability of being in each regime across time, across countries. So most often is the second regime. So you see 2/3 of the time countries are in this regime. So is, let's say is the standard component. So is the normal component, if you want to put this way. And then we have 2 regimes, 2, let's say, kind of time points that are specific. If we observe the first one, the mean is 0 and variance is almost 0. You see? So this is basically a very specific regime. Is a kind of zero inflating component, you see? So my time series probably have many time points, y sub it, in which the variation is 0. It might be because of mistakes, might be because of islands, for instance, that are completely isolated and without cases. So somehow this component adds a component to model the spiky value of the distribution of the density around 0. Okay? The third component, we observe a very large variance. So probably we have very abnormal values in the growth. And this 16% of the time is captured in this component. So notice this. In this way, this is also a kind of dynamic clustering. So each time point of each time series somehow is allocated to one of these regimes. Some country at some point in time was more likely to be here in this regime or here or here. You see, so it's also a different way of clustering. So we are in the bottom level, not at the country level now. Now we can try to combine the two things. I will try to be a little bit brief on this. For example, here I have the dynamics of the Z. So notice this. The marginal distribution of the Z's is this. So let's say the time spent in each regime. But within each cluster, if we split into clusters, for example, you can see the cluster 2 is more likely to be there, you see, than the marginal. But for example, in cluster 3, it's not so often to be in these, you see, and here too. So we can see that indeed let's say the frequency of visiting some states is quite different in different clusters of countries. And then about dynamics. So if we analyze the transition probabilities, we observe, for example, quite different values. I will analyze now more in detail in these next slides. So this is just to illustrate, for example, the first cluster group of countries basically is not so often in the regime 1. Don't forget, regime 1 is zero inflating. So we don't have blacks, you see here. So here is the probability across time of being in each regime or cluster, but we call it regime because it is dynamic. So indeed, this is just, I was just depicting the 10 first countries. So Afghanistan, Angola, and so on. But of course, we cannot analyze all the countries. But well, just for this kind of presentation, it was impossible to do that. So we see that, for example, in this cluster, for example, high probabilities of jumping from regime 1 to regime 2, or from 1 to 3, you see. So it's more often to be in these two, in 2 and 3. Indeed, we can see here, for example, basically we don't have blacks or regime 1 in these two. We have some, obviously, but not so often as we were expecting. In second case, well, we have these stripes. These stripes are a little bit annoying because it's due to the, you see, so without the projection, it's just a matter of graphs. So you see here, we don't have this kind of stripes. It seems that it's changing to a different regime, but no. Basically, this is a very stable cluster. So is the normal cluster. It has quite nice variance to cover, let's say, a broad perspective of growth rates. And notice, so the persistence in the regime 2 is very high. And the probabilities of transition are also quite low, you see? So basically, regime 2 is always the most persistent in cluster 2. So all the countries, let's say, in the cluster 2, somehow are normal, have some normal dynamics, I would say, with big quotation marks. So, and then the cluster 3, also these stripes are a little bit additional. You see that in this cluster 3, it is mostly in the regime 1, you see. Regime 1 is the zero inflating. So might be countries, so we have lots of blacks here, you see. For example, some countries, this might be because of two reasons, and then we have, it's just a kind of detection mechanism. So you may have different mechanisms for this kind of inflating zeros. Might be because indeed, like New Zealand, you don't have cases, or you may have some fraud in this kind of reporting, okay? But you can see different dynamics here too. And you see here, for example, in this cluster is very unlikely to be, or less likely to be in the normal regime. So just moving on, you also can think this kind of clustering because it's two-level clustering. So we have clustering at country level and clustering at the time or the time point level. You can also think it as a multi-level clustering or bi-clustering. So why? Because basically we can group, let's say, one of the dimensions, in this case, countries, into homogeneous groups. So this, here you don't see the stripes, you see. So this is indeed a homogeneous group, excluding here. But overall, it's more likely, even this time series, more similar to this than to this, right? So here you have a group. The difference here is that in typical by clustering, you assume that both dimensions you can reorder or change the order of the columns and rows. And in this case, don't forget here, we have the time. So somehow we can use this model to by clustering, but we can change one of dimensions because you are assuming, in this case, countries don't have a structure, so they are independent. But for example, if you are assuming a component like, for example, spatial clustering, then probably you have the same problem. You can change the order of the clusters. So this is just an illustration. You also can see which countries are more likely to be in cluster 1. For example, we have here New Zealand. We also have France. So you can identify some alerts for some countries. Now I would conclude with some remarks and some extensions. So basically, to sum up and summarize, so I was presenting a possibility, one model of model-based clustering of time series. So assuming this kind of multi-level structure, assuming that is unsupervised. So I don't know the number of clusters and I don't know the number of regimes. I may assume a priori some number. Sometimes we do, but typically we have a problem of model selection as well. So this is an interesting perspective regarding the modeling of the time series dynamics. So you are assuming that within each cluster, different dynamics may be observed. So notice this: if your data set is very diverse, you may need more components. You see, so the number of clusters, S, capital S, number of regimes, capital K, is set by BIC, right? So in some cases, in our case, 3 clusters of countries was able to somehow to depict the heterogeneity across countries or across space. Across time, 3 regimes were also enough, okay? So apart from this point, we also were able to identify, for example, in COVID-19 dataset, for example, some outliers, some zero inflating observations that probably are due to measurement error or some other, let's say, data generating process that we can't grasp. But at least we observe that let's say, if it is from regime 2, it's expected to be normal. If it is from the other regimes, the transitions are not so expected. And that is the reason it creates a second and a third cluster. So basically, this was what I would like to share with you. So basically, we have 2 dimensions, cross-sectional and observed heterogeneity, clustering at upper level. In this, our example was country level. And the clustering of countries is based on similarities of the dynamics within across time. And then the temporal dynamics is based on a latent dynamic variable regime that somehow simplifies the structure, assuming, for example, just 3 clusters. So we have just 3 pure states, let's say zero inflated, outlier state or regime, and a normal state. And you may be, your transitions might be between those 3 in a kind of Markov chain. So notice this, because our model, let's remind that our model is something like this, right? So we have here plenty of flexibility. So typically we obtain a good approximation to the data. So because it's like the first example I gave on cross-sectional with just 2 normals, I was able to fit this kind of skewed histogram. So typically with this model, we can handle skewness, non-normality, heavy tails, for example, inflated zeros, outliers, and so on. Because, well, if you have this outlier group, probably the model suggests an additional component, an additional cluster, an additional regime, just to model that component. And also measurement error issues. So the connection between the latent variable Z or capital Z and the Y's. So now just extensions. So, well, this is a model in which I've been working with some other colleagues. We have many open issues. Now a little bit more on research and further extensions. Well, one issue is model selection. Even with BIC, so some alpha, is still an open issue. The model dimension, as most of you have been working with, is one of the problems in this unsupervised machine learning or statistical learning. So the dimension of the model from simple cases of number of components in PCAs or the number of clusters and so on. So, and it is still an open issue because even in some simulations with these models, sometimes BIC is not completely able to recover the true states. Another issue is that we can, from this model, make extra combinations. I was assuming all these latent variables, the circles, are discrete, right? States or clusters, regimes or states. But for example, these latent variables, some can be continuous, right? So for example, if I don't have this latent variable and I just have this sequence, is just a dynamic factor model or a Kalman filter, okay? So we just have a continuous latent variable. So if you have, for example, these as continuous and these as discrete, is just a mixture of dynamic factor models, you see? If everything is continuous, it's just a multi-level factor model, okay? So we have different possibilities, even combining discrete and continuous latent variables. I was just focused on clustering, and clustering assumes always that we have discrete latent variables. Another possibility is the extensions. So I was giving just a descriptive model, not, let's say, conditional model on covariates. But for example, these y's might be explained by some x variables, right? So what we have here, if you think about this combination, so y is explained by x, y is explained by the cluster, let's call it, or regime, and the cluster also explains or moderates this relation. So basically, if you think just on this combination, this is a mixture of regressions. Within each cluster, I have a regression of the y on the x, you see, and the slope here depends on the cluster. So in some clusters, the slope might be positive. In some other clusters might be negative or insignificant, you see. So this is just an extension, but other possibilities are, for example, these are the clusters, right, of countries, for instance. I may use some time invariant variables, for example, characterizing this latent variable combined together. It's not like after classifying or allocating the observations into the clusters to apply a multinomial log it. No, I don't mean that. It's just one step. So I just have in my model to regress this W conditional on some X. And I have a log link function somewhere in my density to model that part, okay? And sometimes it's useful, for example, to characterize this structure of 3 clusters of countries. For example, could be interesting to have, for instance, a dummy, whether the country is an island or not. And probably one of the reasons of some countries to be together is because they are an island and they can easily control, for example, the number of cases, and probably they can remain stable like New Zealand, Taiwan, and some other countries, okay? Same happens here. So the dynamics can also be modeled by some time varying covariant, okay? And here, well, here might be number of beds, might be some other cases that may explain. Well, just to finish, I don't know how much, well, sorry. So just some references. I'm not giving so technical references, just some overview of interesting books if some of you are really interested in this field. So the first book is a recent book on cluster analysis. So it includes chapters on heuristic clustering, traditional clustering, density clustering, spectral clustering, symbolic clustering, functional data clustering, and so on. So, and also mixture or finite mixture clustering or model-based clustering. So it's a very good book if some of you want to explore this area of clustering. Second one, I would say, is the Bible. So, well, the book is already 20 years old, and it is still the reference. It's a great book. So if some of you want to start really reading a good reference on now parametric or semi-parametric clustering, so it's a good starting point. Then you have a third book, a very recent one. So on model-based clustering and classification. Classification in the perspective of allocation is not exactly on the perspective of supervised learning. It's very interesting book, especially because also includes applications in R. So it allows you to explore. This is a very theoretical book. This is more applied book, and it's very interesting. And then these last two are more on the time series or longitudinal perspective. So these first are more cross-sectional, mainly. These last two are specific to longitudinal data. So this is on hidden Markov models, applications with R, and this is also on hidden Markov models. Sometimes the word hidden can be translated in many different ways. So these models might be known as hidden Markov models, for example, in engineering, might be known, for example, as regime switching models in economics, econometrics, and in social sciences is best known as latent Markov models, okay? Hidden, latent, or regime are all synonyms of the same wording. Well, thank you very much.